Hi everyone, welcome to another video by Cheenta. I am Rajdeep. Today we'll look at a geometry problem which will serve as a example of how configurations, different configurations of the same setup of a geometrical problem can lead to slightly different solutions and modified solutions. And I hope that you learn something and you take something away from it. Let's get into it. Right, so here's the problem. I'll explain the setup. You have a circle, you have a triangle and its circumcircle. The triangle is ABC, and we consider the angle bisector, the internal angle bisector of A. We let that angle bisector intersect the circumcircle at the point D. Then from D, we drop perpendiculars DE and DF onto the rays or lines, in this case AB and AC. The problem is to show that AE is equal to half into AB plus AC. As far as the source is concerned, I am not fully aware of it. One of my students brought it up to me as a problem, and I thought that it was an interesting usage of configuration. And so here we are. As usual, pause the video and try the problem on your own. But one main observation that will go into solving the problem is the fact that, let's get some of the basic stuff out of the way. You have angle bisector and you have a point on the angle bisector from which you drop perpendiculars. It's not very hard to show. It's basic congruence, that since these two are the same angle, these two are right angles, and you have a common side. In particular, since it's a right angle, these two angles are also equal. So by angle side angle congruence criteria, these two triangles are congruent, and so AE is equal to AF and DE is equal to DF. But you could also think of it as remembering the fact that the angle bisector is composed of exactly those points which have the same distance to the two lines that form the angle. That's one of the definitions of the angle bisector. So in that case, this is actually trivial. But we get two things for free right away, simply from the fact that we have an angle bisector and we have perpendiculars that we've dropped from. We get AE is equal to AF and we get DE is equal to DF. You could imagine that this will play an important role. Since AE, we want to show that AE is half of AB plus AC. It's the average. So if we have some sort of a control between the two sides, that could be very helpful. And AE is equal to AF is exactly that. And we get DE is equal to DF. Doing this, you have not used the fact that D is a special point. These two facts are true for any point D on the angle bisector. So as usual, in all of my videos where I solve our geometry problem, the flow of information is extremely important. What have you used? What have you not used? Degrees of freedom and such. So information is extremely important, and so you don't want to miss out on using the fact that D is a special point on the angle bisector. In particular, it's a point on the circumcircle of ABC. This is where we use a well-known fact in geometry that's not very hard to prove, which is that if you take the circumcircle of a triangle, forgive my bad drawing there, and you take the angle bisector and you intersect it, then this point is actually the midpoint of the arc BC not containing A. Why is that? Very simple. This is because since this is an angle bisector, this angle is equal to this angle, but since A, B, C, D form a cyclic quadrilateral, this angle is equal to this angle, and this angle is equal to this angle. So DBC is equal to DCB, or DB is equal to DC. It's an isosceles triangle. So in particular, D is the midpoint of this arc, and this is extremely useful for us. DB is equal to DC. So this gives us something very nice. And also, why? So I'm going to make a jump here, and I'm trying to justify why that jump is a reasonable one. Why you would look for it in the first place. You have something about AE already. You want something about AB, and since you have AF, something about AC. What's the missing link? The missing link is either BE or CF. If I could get more control over these guys, I would be closer to solving the problem. So, and this is where we make our first leap, so as to speak. In that, you connect D to B, you connect D to C, and we have something nice, which is that DB is equal to DC, right? And DE is equal to DF. Two sides common and a right angle. So by the RHS criterion of congruency, or whatever, there's many ways of going around this. the way to think about congruency criteria in general is, given the information that is common to the two triangles, so say two sides and an angle, if I had that information, so like those were fixed lengths, right? So if I gave you that DB is this fixed length, DE is this fixed length, and I have a right angle, is that a unique triangle? And in this case, it's true. It's very easy to see that it will be a unique triangle. If you fix the perpendicular, fix the hypotenuse, you're also fixing the base. So then it's just SAS criteria, right? Same, yeah. So that's a very easy way to see this. In particular, we don't even need to use congruency actually. Since the hypotenuse are the same and the perpendicular are the same, we get that BE is equal to CF. This is either by congruency between triangle DBE, congruent to triangle DCF, or by just noticing that BE is the base in this right angle triangle, in these right angle triangles where the hypotenuse and the perpendicular are the same. So by Pythagoras' theorem, if you will, they're the same. Now BE is equal to CF is a very nice fact when you can combine it with AE and AF. Think about what's happening here. You want something about AB and AC. You have something about AE and EF. This B is equal to CF is the thing that we were looking for. It was connecting AE and AF to AB and AC. And we'll see that that's actually enough. In particular, AE is equal to AF. AE is what? In the configuration that I've drawn, so this is where the whole thing with configurations comes in. AE is equal to AB plus BE, right? Since E is outside the segment. Whereas AF is equal to AC minus AF, since F is inside the segment. AB plus BE is equal to AC minus CF. But since B is equal to CF, I get AB is equal to AC minus, let's say, 2BE. Right? In other words, BE is equal to AC minus AB by 2. I'll just move things around. But what does this mean? This means that AE, which recall is AB plus BE, is AB plus AC minus AB by 2, or AB plus AC by 2. Now you might say, okay, where this was just a nice geometry problem. What does it have to do with configuration? What it does have to do with configurations is that if I drew a different diagram, see, in the question it never said what angle was less in ABC and what angle was more. It didn't say B is greater than C or B is less than C. I drew the diagram in such a way that I got this calculation. If I drew it in another way, think about so in this case angle B is more than angle C. Right? It's tapered towards B. If I drew a different diagram, something which was leaning towards C, you would see that D is a point here, and so in this case E is inside the segment and F is outside the segment. In which case, what would happen? This would be a minus sign and this would be a plus, but it would give you the same result. The only case where you get something weird is if both of them are outside. So E is outside and F is outside, right? So by some miracle, it so happens that both the perpendiculars are outside. But if that was true, what I would get is that the signs are equal, right? So either I would get AB minus BE is equal to AC minus CF, right? Because up until this, there's nothing configuration specific. We've done a very general calculation up until this part. But since B is equal to CF, this actually tells me that AB is equal to AC. Or that the only way you can have perpendiculars from B onto AB and AC be both outside or both inside is if ABC is isosceles. So in this case, you get something funny in that if ABC is isosceles, this is a useless statement. It's saying nothing to me, right? This is equivalent to B is equal to CS. So if I started with an isosceles triangle, I would achieve nothing new. So you would say the proof breaks down. It does not, thankfully. So if ABC is isosceles, then indeed, it's not very hard to see that the perpendiculars. So let's actually start with the isosceles triangle. Forgive my bad drawing once again. But something more interesting happens this time. The angle bisector is also the perpendicular, is also the median. So this is a split right down the middle. It's a diameter. And in this case, because it's a diameter, these two angles are right angles. So in this case, B actually coincides with E and F actually coincides with C. In particular, AE is just AB and AB is equal to AC. So in this case, you just get AB, AE is equal to AB is just half into AB plus AC, since AB is equal to AC. So it's just twice into AB. So there is a configuration issue here that if you start with an isosceles triangle, this statement gives you nothing new. So the proof comes to a halt. But in the case where the proof gives you nothing new, the problem is actually trivial. Yeah, so I hope you got a feel for how configurations can change proofs. In particular, the isosceles case here is actually completely separate. The proof line does not move forward. But whenever there's an issue with this plus minus, something known as directed lengths, so directed lengths is actually very helpful because it takes away the ambiguity in the sign. And so in that, BC is actually minus CB. We usually write them as vectors because vectors are actually directed. And in that case, if you write a very careful proof, they show the sign goes away. But the isosceles case is still separate. To see like a good exponentiation of directed lengths and even directed angles, one can go to the book Euclidean Geometry in Mathematical Olympiads by Evan Chen. There's a good exposition on directed lengths and directed angles in that book. And these kinds of like directed arguments take away configuration issues for the most part. And that's it. I hope you enjoyed the video. Thank you so much for watching. Bye-bye.